Electronegativity tells us how strongly an element can pull electrons. And these are the numbers that has been assigned based on electronegativity of different elements. The larger number means greater electronegativity. That means fluorine is about 4 times, more than 4 times, stronger than sodium, which has 0.9. Now you get these values from electronegativity table given in the book. Sometimes just by looking at periodic table and the location, you can tell which one has higher electronegativity and which one has lower electronegativity. It increases as you go from bottom of the periodic table to the top and to the right. And I'm going to show that to you in next slide. You're looking at a periodic table and electronegativity increases along this direction. So let me show you that. Now there could be a few exceptions, but in most cases it's going to work. So this is the direction in which electronegativity increases. That means lithium has a lower electronegativity than nitrogen. Oxygen has a higher electronegativity than nitrogen, and fluorine has a higher electronegativity than oxygen. So in other words, fluorine is, in this case, has the highest electronegativity. That means it can pull electron most strongly toward itself. Again, here we're showing you how this electron gets shifted. This represents sodium with 0.9. This represents Cl with 3.0. Now again, by looking at periodic table, you can also tell that Cl is stronger than sodium, but you may not know how much stronger. For that, you need to look at the values. Sometimes if it is far right, except the noble gases, which do not show any electronegativity. But on the right hand side, elements are more electronegative than left hand side. So this is coming from far right end, and this is coming from the left, far left. So that's why this has a much lower electronegativity value than this. Now if you put those electron pairs somewhere here, now Cl being much stronger, and the difference in this case is more than 1.9, so obviously you'd expect this electron pair would be completely shifted from center towards Cl, and that would give Cl a negative charge, and sodium is going to lose its share of electron, so sodium would become sodium plus. Now that's what we're showing you again here. Electronegativity difference in case of sodium and fluorine is even larger than that. It's 3.1, which is greater than 1.9. In order to be ionic bond, electronegativity has to be 1.9 or greater. So in this case, it's more than 1.9, which is 3.1, and that makes sodium plus. And fluorine got the extra electron because this electron pair goes towards fluorine, which is much stronger. And fluorine, because of this extra electron means originally this electron came from sodium, and the other electron that fluorine already had. And so both electrons it gets closer to itself, and it gets so much closer, so it becomes fluorine minus, it becomes its own electron, and sodium becomes sodium plus, and this kind of bonding is called ionic bond. So keep that in mind when there is a large electronegativity difference, like more than 1.9. 1.9 is considered to be like a ionic bond too, but in most cases we go by greater than 1.9. What would happen if electronegativity difference is 0? Like in this case, two fluorine bonded together, they're equally strong, even though each fluorine is 4.0, but they're equally strong, so electron pair would be sitting in the middle. No one is going to win, and that's called covalent bond. In between 0 and 1.9, if electronegativity difference is greater than 0 but less than 1.9, we call it polar covalent bond, or simply a polar bond. In this case, I'm copying this number from electronegativity table. Carbon has 2.5, oxygen has 3.5, so the difference is 1.0, and it is less than 1.9, so obviously it's not going to be an ionic bond, rather it's going to be a polar covalent bond. In polar covalent bond, again you can consider that initially electron pair was sitting in between, but since oxygen is stronger, so obviously the electron pair would be shifted towards oxygen. The difference is here the difference is not big enough. So in other words, it would be shifted towards oxygen but would not become 100% on oxygen to get minus charge. So rather it would develop a little bit of negative charge on oxygen end, we call it delta minus, and a little bit of positive charge on carbon end, so that gets delta plus. And in organic chemistry, this is called inductive effect. So by simple bond formation with electronegativity difference, one end can get slightly negative, the other end can get slightly positive. And then direction of polarity would be from positive towards negative. It's always that the case, so this is how we get the direction of polarity. This is also the direction toward which pair of electron gets shifted. Now here we're going to discuss acids and bases and different definitions. Bronsted definition of acid is the substance that donates H+. A base is a substance that accepts H+. So the reaction that is given here, how do I know what is happening? Let's first focus on this compound. And from the similarity, you can focus on this compound, on the product end. Now look at how are they different. Here, this end doesn't have hydrogen anymore. That means this compound lost hydrogen. So that means it donates hydrogen, and that's why it's an acid. Now what has accepted H+? Again, look at changes here. From started like this as OH-, ended up with H2O. That means this has gained one H+. So that means this absorbs H+ or accepts H+, so that's why it's acting as a base. Now on this end, we are labeling this as conjugate base. Conjugate base is formed by removing hydrogen from an acid. So we removed hydrogen from this end, and that's why it becomes conjugate base. Conjugate acid of a base is formed by adding H+. Here in this case, you're adding H+ to this end, and that's how you got conjugate acid. In Chem 112 also, you're going to learn the same thing like conjugate acid and conjugate bases, where you just, by adding H+, you get conjugate acid. By removing H+, you get a conjugate base. A strong acid means weak conjugate base. Now, let's try to think about this. A strong acid means it can readily give up H+. On the other hand, if it becomes a base, if it readily accepts H+, it would no longer be a strong acid, because a strong acid would like to get rid of its H+. So in other words, if I have a strong acid which shows great tendency to donate H+, it would give relatively weaker conjugate base. So keep this in mind. Strong acid means a weak conjugate base. Which weak conjugate base means it's the compound that doesn't like to grab H+, doesn't like to hold on to H+ that strongly. Now here we're showing you expression which is called Ka. Now the product of this reaction, this is an acid reacting with water, gives you A-. This is a symbolic representation of an acid other than actual formula. And H3O+, that's how water changes to when it takes H+. So this gives H3O+. So now you'd have products on the top. This is how we write down equilibrium constant or acid dissociation constant. H3O+ on the top, A- on the top, and then HA on the bottom, and H2O concentration on the bottom. Now usually water is in excess, so often we ignore this remaining constant. So you'd mostly have those three numbers on the top. Now, keep this in mind. If I have a stronger acid, this would break down and that would give me a larger concentration of H3O plus. The stronger acid means more of these would break down. And if I have larger H3O plus, so this number is going to go up. That means my Ka value would increase when my acid is stronger. Now, we also define what is called pKa, which is defined as log of inverse of Ka. So if Ka is large, pKa is going to be small. Keep in mind, Ka large means strong acid. Said when large Ka. Now, large Ka means small pKa. So large Ka means small pKa. So now what we understand here is, if I have a stronger acid, that would have a smaller pKa. Again, in organic chemistry, often you would see pKa values. This is coming from your homework. Formic acid with pKa value of 3.75, picric acid with pKa of 0.38. Which one is the stronger acid? Since this has a smaller value of pKa, so this is a stronger acid, and formic acid is a weaker acid. The question is also asking for Ka value. So this is how you can set it up. I can just show you one of these. Minus log of Ka, this is at base 10, equals to 3.75. So most of you have scientific calculator, and so you can always, if you want, you can write down one additional step. Log 10 minus 3.75. So basically this is 10 to the power minus 3.75. So if you have the scientific calculator, often it's the second function of minus 3.75, second function log of minus 3.75. And that would give you the Ka value. This is log of Ka. So from here, Ka, mathematically this is going to be 10 to the power minus 3.75. So you can use your calculator to get this value. Sorry, I'm trying to fix this 3. Now Lewis's definition of acids and bases. An acid accepts electron pair and a base donates electron pair. So how would I know whether what is going to act as a base and what is going to act as an acid? We already know how to write down some of the compounds. Like nitrogen neutral compound would have 3 bonds and a pair of electrons. So this is trimethylamine, and this is 1 pair of electron on nitrogen, because you'll have to have 1 pair of electron on nitrogen because you need to have 8 electrons. This accounts for 2, 4, 6 electrons, so that makes 8. So since it has a pair of electron, it can donate. It's like somebody has money, can donate that money. So if you don't have electron pair, you cannot donate electron pair. Now aluminum chloride, on the other hand, has only 6 electrons. Naturally, it doesn't have 8 electrons, even though it would love to have 8 electrons. So this is like one of the exceptions when you write down Lewis structure. So in a reaction like this between AlCl3 and NCH33, this electron pair is donated to aluminum, and aluminum happily accepts electron pair because every element would, other than hydrogen, would like to have 8 electrons. So that's how you get AlCl3, and here you get NCH33, and then there is a bond in Al with Al. Now pay attention to this development of positive and negative. Now in next section we'll be discussing that in details, and these are called formal charges. So we'll explain that quite soon. But there are 2 ways to do that. You can do a calculation based on valence electrons of nitrogen and then how many of these shared electrons are there, or you can keep track of who is losing electrons and who is gaining electron. In this case, nitrogen is losing electron to aluminum It's basically sharing. Initially it was not sharing with anyone, then it was sharing. That means it got half of that share. That means it got one share. So that means it lost one of its electrons to aluminum, and that's why it developed plus. And aluminum got extra electron share, extra share of one electron. That's why it got minus one. That's one way of looking at it. And we'll show you in next section how to calculate these formal charges. That way you're not going to make mistake.